Welcome to part B of the chapter 3 lecture for the EE111 lecture series. To begin, we talked last time about a collection of resistors being in series. And one of the things that's most important for us to find, if we have a known voltage across a collection of resistors that are in series, it's quite often useful for us to find what's the voltage across one of those resistors. This is a common question, and it's what brings us to this technique called voltage divider. And all the techniques we talk about today are techniques that these are sort of quick shorthand ways of, rather than going through, all of these you could do using Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. But we're presenting these now as actual specific techniques that you can go to, that you have a quick equation where you don't have to necessarily go through all those steps. You can sort of quickly find a solution. And this problem of we have a known voltage across a collection of series resistors. We want to know the voltage across one of those resistors. This is one we solve using voltage divider. So to jump right into the problem, we have a circuit up here, shows a known voltage across a collection of series resistors. And we saw in the last video how to find the equivalent resistance of these resistors. So in this case, Req is going to be R1 plus R2 so all the way to Rn. We don't know, there's some unknown number of resistors, but the equivalent resistance is going to be the sum of these resistors. We know also that if we have this voltage V applied across this resistor collection with resistance Req, that the current, we know because V equals I times Req, we know that the current is going to be I equals V over Req. We further know that if the current through all of these resistors is V over Req, that the voltage across any one of these resistors is going to be that current times the resistance. So we know that for any particular resistor N, the voltage across resistor N is going to be I times Rn. So the voltage across resistor N, so now actually I think the book says X. Voltage across resistor X is equal to the total voltage, where this V here is the total voltage across all of these resistors connected in series, divided by the equivalent resistance of, the total voltage times this ratio Rx, the resistance of the particular resistor we're trying to find the voltage across, divided by the total resistance of all those resistors. This is the voltage divider formula. The voltage divider formula says, find the voltage across one resistor, you take the total voltage across all of them, times the ratio of the resistance of that resistor divided by the total resistor, the total series resistance. So what about resistors connected in parallel? Well, this technique is great. We have this quick equation here to find the voltage across one resistor when they're connected in series. Is there an equivalent equation for resistors connected in parallel? Well, the question of finding an unknown voltage across resistors in parallel is usually not an interesting one, because one of the features of resistors in parallel is they all have the exact same voltage across them. So typically you're not actually trying to find the voltage across a particular resistor connected in parallel, because if you know the voltage across all of them, you know the voltage across all of them. So, okay. Current divider. Current divider is a similar technique, is something we want to find with resistors in parallel. So in the case of resistors in series, the current through them is kind of boring because it's all the same. And in the case of resistors in parallel, the voltage across them is kind of boring because it's all the same. But in the case of both voltage across resistors in series, which we just talked about, that's voltage divider, current through a particular resistor in a parallel collection of resistors is also a very interesting thing for us to find. So in this case, we have a collection of resistors all in parallel. We have a known current flowing through all of them, and we want to know what's the current flowing through one of those branches in this parallel collection. We're going to basically analyze this the exact same way we did the voltage divider equation. And you'll find that the solution for these, anytime we have a sort of a current equivalent of voltage, parallel equivalent of series, the analysis is always going to be very complementary. So basically, rather than a KVL, we do a KCL. Rather than doing a parallel collection, we'll do a series collection. Things like, we're always going to use the complement to find the solution. So if you know the solution for the series version, try to think about the complementary approach to finding the answer for the parallel one. Okay, so we have this known current I flowing through all of these. We want to know what's the current flowing through one of these resistors. We call it RJ here. I don't know if it's labeled in the previous one. No, going back now. So we have this N resistors. Now we know the expression for the total voltage across, oh, sorry. Let me go back here. So we can find an expression for the voltage across all of these using Ohm's law. So basically we know if we know the total resistance here, which is this equivalent parallel connection of resistors, and we know the current flowing through them, we can find the voltage across all of them. All right, so let's do that. So Req 1 over R1 plus all the way to 1 over Rn. I'm not going to write it to the -1. That's our Req. From now on, we're just going to call it Req because I hate writing this big, long expression. We know that V, the voltage across all of these resistors now, is going to be I times Req. So that gives us the voltage across any and all of these different parallel branches. But remember, the question we're trying to find is what's the current through one particular branch? What's this current IJ through resistor J? Well, if we know the voltage across RJ, and we can just find this current using that resistance RJ. So we can just use Ohm's law now to finish this up. So we know this is the voltage across all of them. So we know the current through the current IJ through the jth resistor is going to be the voltage across that resistor, which is going to be I times this equivalent resistance, divided by the resistance of that resistor RJ. So you'll notice the similarities and differences with these expressions. So in this case, for the current divider, we have the current of a particular branch is equal to the total current times some ratio. That's very similar to voltage divider. Voltage divider was the voltage across a particular resistor was equal to the total voltage times some ratio. But you'll notice the difference. In the case of current divider, we have the equivalent resistance on top and the resistance of the particular branch on the bottom. If we went back here, we had the resistance of the particular branch on top and the total resistance on the bottom. So they're flipped, and it makes sense. There's lots of ways to think about it. There's lots of ways it makes sense. But the one I always like to think of is, remember what we talked about equivalent resistance. We said the equivalent resistance always of parallel resistors always has to be lower than the lowest resistance in the branch. So if Req is going to be lower than the lowest resistor in the branch, then this ratio always has to be less than 1. So Req divided by the resistor of any one particular resistor in the branch always has to be less than 1 because Req has to be lower than the lowest resistor in that branch collection, in that collection of parallel resistors. Why is being less than 1 important here? Well, because we're looking at what fraction of the total current is this particular current going through any branch. If we had more current flowing through one of the branches than we had flowing into this collection of branches, something would be really very wrong here because these are just resistors. There's no current supplies, there's no voltage supplies. This is, the resistance through any one of these branches is always going to be less than the total, the current through any one of these branches is always going to be less than the total current flowing into this collection of branches. So therefore, this ratio here had better always be less than 1. Okay, so that's the background on it. We're not going to belabor that anymore. Let's do some examples. So let's do some examples. I feel like I missed a... Did I not have a voltage divider example? Huh. I think I'm missing a slide here. Oh, well. We'll do what we can. We'll do a voltage divider on this one. Yeah, we'll do both. We'll do a voltage divider on this one too. Okay, so current divider. So we have a circuit here. We have this known 8 amps flowing into this collection of, now one thing to note is this is a collection of branches. Right? We have four branches, but they're not just a resistor. They're right? This is not as simple as just it's 4 resistors and find the current through one of them. This is, we have 4 parallel branches, but we're going to have to do a little bit of math here to find out what the actual resistance of this collection of branches is. And we know how to do that. We did that last time. So our question is, we're going to try to find this current IO through this 24 ohm resistor in this collection. So the first thing we're going to do is we're going to find the resistance of each one of these branches. So we're going to take these branches, combine them, and combine the resistors in series. So to do that, we have here we have 36 plus 44. That's going to equal 80. And then we have 10, and then we have 40 plus 10 plus 30. That's going to equal also 80. Getting interesting here. So we can redraw this circuit as an 8 amp supply flowing into, we have an 80, a 10, another 80, and then the 24. Okay. And we want to know what's that current there. So we're going to use current divider to find that. Okay, so we have, so how are we going to do that? First thing you have for current divider, we got it, and for voltage divider, first thing you got to do is find the equivalent resistance. We did part of that. We took the resistors in each one of the branches and combined them to find the resistance of the branch. But now we need to find the equivalent resistance of all of these. So the equivalent resistance in this circuit is going to be this parallel combination of resistors. So that's going to be 1 over 80 plus 1 over 80 plus 1 over 10. I got them out of order here a little bit, but that's okay. Plus 1 over 24. -1. Let's talk about that though. I got them out of order. So when I'm analyzing resistors in series or in parallel, does it matter if they're out of order? It doesn't actually, because mathematically, this is just a summation. And what do we know about summation? You can switch the order of things in a sum. Same with resistors in series. Resistors in series, we're just adding their resistances. So mathematically, we can switch around the order of those, of a summation, right? What is that? That's the commutative property of addition or something. It's been a long time since I learned those names for those things, but I think it's commutative. That sounds about right. It is now, the commutative property of addition. We can switch those around and it doesn't change the overall result. And what that means for analysis is, yeah, you can switch the order of things in series or in parallel and it doesn't change the equivalency of those things. Sometimes there's a specific configuration you're trying to analyze and therefore you got to keep it in that configuration. But for the equivalency of the math, for equivalent resistance, it doesn't matter. And that makes sense if you think about this circuit, right? If we think about this circuit as actual branches of resistors physically floating in air, if I took these branches and I kind of bent the wires around and bent them in different directions, would that matter? No, it's going to be the same thing. So it's going to be fine. So yeah, so things in series, branches in parallel, we can switch the order and it doesn't change things. Okay, anyway, we found this REQ. I'm going to do the math really quick here on the old trusty HP. And I get 6. Sanity check now. 6 should be lower than the lowest resistance in this branch. Is it? Yes, the lowest is 10. 6 is less than 10. Doesn't mean we got the right answer, but it means we don't for sure have the wrong answer. All right, so REQ was 6 for this circuit. So now let's go back to our current divider equation. Current divider equation says if our equivalent resistance is 6 and our total current is 8 and our branch that we're interested in is resistance 24, that the current IO, that's the current through the 24 ohm resistor, that is going to be the total current, which is 8 amps, times the equivalent resistance of the circuit, which is 6, divided by the resistance of our branch, which is 24. And that, if I don't have to go to the calculator for this one, this should be 2 amps. And so we should have 2 amps flowing through that branch. Okay. But there's some other things we can say, right? We already found the equivalent resistance of this circuit. It's 6. So I'm going to try to shoehorn a voltage divider problem because I didn't leave an example for voltage divider in here. So if we know that the equivalent resistance of all of this, and let me change my color. I'm going to start to make a mess here. So if we know that all of this is 6 ohms, and we have 8 amps flowing in it, then what's the total voltage across here? What's this voltage across this whole shebang? Well, that voltage should be 8 amps times the equivalent resistance, which is 8 times 6, which should be 48 volts, right? So we know that there's 48 volts across here, which means there's 48 volts across here, 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 right? We got one node up here, one node down here, there's 48 volts across it. So each one of those branches, there's 48 volts across it. So now my question is, I ugly this thing up quite a bit here. Let's clean it up. See. Magic of technology here. Okay, so I know now that we have 48 volts across this thing. And my question is, what's the voltage across this particular resistor? Now I have a known voltage, 48 volts, across a collection of series resistors. These series resistors are the 40, the 10, and the 30. So if I want to know the voltage across one of those, I can use voltage divider. So voltage divider tells us that if we have a known voltage, 48 volts, and we're trying to find the voltage across one resistor in a series collection, the voltage across that resistor, so the voltage across the 30 ohm in this case, is going to be the total voltage across the whole collection, which is 48 volts, times the resistance of the resistor in question, which is 30 ohms, divided by the total resistance of the branch, which is 40 plus 10 plus 30, but we already solved it. It was 80. And that should give us, well, it better be 18, but let's just sanity check ourselves here. If it's going to be on the internet, better make sure we did it right. And it is 18. So we were able to use voltage divider to find the voltage across this particular resistor. And that was, again, we did a little bit of combining resistors here. We found the equivalent resistance. Finding the equivalent resistance both allowed us to find the voltage across all of these, and it allowed us to use the current divider. And once we had the voltage across this series branch of resistors, we were able to use voltage divider technique, the voltage divider equation and technique, to find the voltage across one of those resistors. Now that we've talked a lot about resistors in parallel, resistors in series. We've talked about the effect of combining resistors in parallel, the effect of combining resistors in series. Let's talk a little bit about, let's get down to kind of brass tacks here and talk about measurement. So when you're measuring something, when you're measuring a current or a voltage, you have to have a meter, and the meter basically has to be able to feel what the particular quantity you're measuring is. So if you're measuring voltage, what is voltage? Voltage is an electrical potential between two different locations, right? It's a potential difference across things. And because voltage is this potential difference between two locations, your meter is going to have to connect to measure voltage. If we're trying to measure the voltage across R2, your meter is going to have to touch it's going to have to touch, that's a meter, folks, that's a meter. It's like a Game Boy with a cherry on the screen, I don't know. So it's going to have to touch these two nodes, right? In order to feel what this voltage is, in order to feel this potential difference between two locations, the meter's got to touch those two locations. And so the question is, you're basically taking this meter and you're putting this meter in parallel with your resistor. So if our meter has some equivalent resistance, if our meter internally behaves like it's got a resistor in there, which they do, real meters do we want this resistor to be very large or very small? And I'm saying this meaning, if we're trying to minimize the impact that the meter has on the circuit, Do we want this meter's resistance, measuring voltage, across the resistor, across the wherever we're trying to measure the voltage? Do we want this meter to have a very high or a very low resistance? Pause the video, answer the question, be honest. Okay, did you say it should have, a lot of people instinctively say it should have a low resistance. You know, people think, you know, low resistance, we don't want it to resist things. But what happens here? If this meter has a low resistance and we're putting it in parallel with R2, that resistance is going to wipe out R2. Because remember, the resistance of things in parallel is always less than the lowest value. So if this meter has a low value, it's the total resistance is going to be less than that. So basically, almost all the current is going to flow through the meter instead of R2. It's going to impact our circuit substantially. It's going to change the effective resistance of that R2 region. It's going to have a big impact. So for measuring voltage, for a voltmeter, we want R to basically be infinite. We want R to be as big as possible. We want the resistance of a voltmeter to be very, very, very large. And if you think about it, that's how we minimize impacting the circuit when we're connecting things in parallel. If you think about it, everything is in parallel with a really big resistor, right? You know, any resistor you have in air, the air around us is a resistor, right? It's a very, very, very large resistance resistor, but it is, right? So everything is in parallel with the air. You know, there's carbohydrates in the air that collect on the surfaces of things. It's just a very high resistance. So it doesn't have much of an impact on things. And that's what we want. If we want things in parallel to not impact things much, we want them to have a high resistance. But what about measuring current? For measuring current, you know, current is the charge flowing through a region of a wire per unit time. So most current meters have to actually sort of insert themselves, right? And the current meter has to, in order to measure a current, you have to break the circuit and insert your meter in between. And what that will do is it will allow, let's do another meter here. There we go, it's a little better. That will allow whatever current was flowing through here to go through the meter and then back in through the circuit. And by doing that, by forcing all the current to flow through the meter is actually able to measure what that current is. Now, so in this case, a current meter has to be connected in series. So if a current meter is connected in series, do you think we want it to have a very big resistance or very small resistance to minimize the impact of the circuit? We want it to have a small resistance because remember, resistors in series, their equivalent resistance adds. So if we're adding a resistor value to the resistance of our circuit, we want that resistance that we're adding to be as small as possible. So for a current meter, we want R to approach 0. An ideal current meter would have a resistance close to 0. And I'm guessing if we switch to the next slide, I will have neatly assembled all of these things that I just talked about because I jumped ahead and I could have just relied on this slide. There we go, look at that. So yeah, if we are measuring, I do this all the time. I talk the slide ahead on the slide before, it's fine. So if we are measuring current, it's gotta be in series and we want this to have a very small resistance. If we're measuring voltage, we want this to be in parallel. And we want this to be a very large resistance if possible. But we know that in reality, we're not actually going to get that. We're not actually going to attain a 0 ohm ammeter. A current meter is called an ammeter usually. We're not going to be able to get a infinite resistance voltmeter, but we can get fairly close. So for instance, for the boards that I designed, and I'll post a video kind of talking about them, for the boards I designed for this class, they do have an onboard voltmeter and current meter. A voltmeter and ammeter, and the resistance of the voltmeter is 1.2 mega ohms, and the resistance of the ammeter is about 4 ohms. Now that's a fairly high resistance for an ammeter, but there's a reason it's designed that way. The circuit in general is only meant to use large resistances. It's not really meant to have massive current. So we're going to be measuring circuits that have resistances in the kilo ohms. 4 ohms isn't going to have a huge impact, but it will have an impact. And part of your lab will be to calculate what that impact of the measurement is. But it should be noted, ammeters and voltmeters do impact the behavior of a circuit slightly, To minimize that impact, ammeters should have a small resistance, voltmeters should have a large resistance. Also, voltmeters are always connected across the terminals where you're trying to measure voltage. Ammeters always require you to break the circuit and insert the ammeter in the circuit to sort of force that current to flow through the meter itself. Now, some of you might say, oh, what about the cable clamp ammeters? Yeah, there's ways to measure currents. There are other ways to measure currents. But for the methods we're talking about a series ammeter, the types of meters you'd use in class, types of meters you will use in lab. These are the types that actually, they actually divert the flow of current through the meter and actually measure it there. So, okay, so we've talked about combining resistors. We've talked about analyzing resistors or analyzing circuits. We've talked about voltage divider, current divider techniques. So let's apply that. Let's apply voltage divider, current divider. Let's try to find this current IO in this circuit. So yeah, it looks like we got a lot of resistors. We got to clean these up. So let's combine these resistors a little bit to clean up. We're trying to measure IO, the current through the 600. So let's leave this one alone and let's combine everything else. So do we have any resistors in series? Doesn't look like it. Okay, is the 20 in series with the 50? Nope, it kind of looks like it's in series, but it's not really in series because there's that little thing. What about parallel? Well, it kind of looks like this is in parallel with this, but they're not because there's this thing in between. These kind of look like they're in parallel, but they're not because, there's the other one there. There's no resistors in parallel in this circuit. And there's no resistors in series. So for this circuit, we actually can't simplify it at all. And that's because this circuit has a feature which we haven't talked about yet, which, just to whet your appetite here, this is going to be the subject of the next lecture. So I will see you on part C. Welcome to part C. This is the last section of the